Nanomechanics stands at the thrilling frontier of science and engineering, offering unparalleled insights into the mechanical behaviors of materials at the nanoscale, where the rules of the macro world no longer apply. What makes nanomechanics uniquely fascinating is its ability to exploit the high frequencies of nano devices. These devices' resonant frequencies can be tuned to detect the presence of minuscule particles, even individual molecules, transforming the way we sense and interact with the microscopic world. Utilizing tools like the atomic force microscope, researchers can now probe the very bonds that hold molecules together and map the surface roughness of materials with astonishing precision. The study extends to the nanomechanics of thin films, where the arrangement of grains within alloys can bestow extraordinary properties, opening doors to materials that defy traditional limitations. Moreover, the field is pioneering the development of nanomachines, cars, motors, and robots at the nanoscale that can move and perform tasks, potentially revolutionizing medicine, manufacturing, and beyond. This convergence of disciplines and technologies not only underscores the unique allure of nanomechanics, but also heralds a new era of innovation where the smallest scales unlock the greatest potentials. Nanomechanics, a subdiscipline of nanotechnology, followed closely behind. This field emerged from the realization that the mechanical properties of materials can drastically change when scaled down to the nanometer range. Key milestones in the development of nanomechanics include the discovery of carbon nanotubes in the early 90s, the development of the atomic force microscope, and the groundbreaking work on graphene, a single atom-thick layer of carbon atoms, which was rewarded with the Nobel Prize in Physics in 2010. These breakthroughs have paved the way for a wealth of applications, from stronger, lighter materials to more efficient energy storage systems and even revolutionary medical treatments. To comprehend nanomechanics, we first need to understand the basics of quantum mechanics. Quantum mechanics, the fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles, is a critical piece of the nanomechanics puzzle. It's like the language that nanoscale particles speak, a language of probabilities and uncertainties, of superpositions and entanglements. Quantum mechanics tells us that at the nanoscale, particles can exist in multiple states simultaneously, only resolving into one state when observed. This is the principle of superposition. Imagine a nanoscale object that is both here and there at the same time, only deciding where it truly is when you look at it. This kind of behavior is utterly foreign to our everyday experience, but it's business as usual at the nanoscale. Another quantum oddity is entanglement. Two particles can become entangled such that the state of one instantly affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, has profound implications for nanomechanics and the design of nanoscale devices. Now let's talk about mechanical properties at the nanoscale. Stiffness, strength, and elasticity. These are all properties we're familiar with in the macroscopic world. But at the nanoscale, things aren't quite so straightforward. For instance, materials that are brittle in our world can become ductile at the nanoscale, able to be stretched out without breaking. This is due to a decrease in defect size and an increase in surface-to-volume ratio as we go down in scale. Similarly, materials that are soft and squishy to us can become incredibly stiff and strong at the nanoscale. In the nanoscale universe, we observe that properties of materials can change drastically, opening up a realm of new possibilities. Understanding these quantum and scale effects is crucial to manipulating materials at the nanoscale, and thus to the field of nanomechanics. So as we delve deeper into this fascinating world, we're not just shrinking our perspective, we're expanding our understanding. Now, let's explore the wide range of unique materials that exist at the nanoscale. In the realm of nanotechnology, we encounter an array of captivating materials, each with their own unique set of properties. These nanomaterials, measuring in at less than 100 nanometers in at least one dimension, include nanoparticles, nanowires, nanotubes, and graphene. Nanoparticles, the smallest of the bunch, are like the building blocks of the nano world, used in a variety of applications from medicine to cosmetics. Nanowires, as their name suggests, are wire-like and used in electronics due to their excellent conductivity. Nanotubes, hollow cylinders with extraordinary strength and conductivity, are the superheroes of the nano world, with potential uses in everything from space elevators to water filtration systems. And then we have graphene, a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, which is incredibly strong, flexible, and the best conductor of heat we know of. But how do we know about these impressive properties? Well, it's all down to mechanical testing methods designed specifically for nanomaterials. These tests examine a material's mechanical properties, such as its strength, elasticity, and stiffness. These properties can be vastly different at the nanoscale compared to the macro scale due to the effects of quantum mechanics. Methods such as nano-indentation, where a tiny indenter is pressed into the material's surface to measure its hardness, and tensile testing, which pulls on the material to measure its breaking point, are used to test these properties. There's also atomic force microscopy, a technique that allows us to even image the surface of these materials at an atomic level. It's important to remember, though, that the behavior of these materials can significantly change depending on their size, shape, and environment. This is due to the surface-to-volume ratio becoming increasingly significant as we go smaller, and quantum effects becoming more prominent, leading to some truly unique and fascinating properties. From nanoparticles to nanotubes, these materials possess remarkable properties that can be harnessed in numerous ways. How do we measure properties at the nanoscale? One word, AFM. That's atomic force microscopy, a powerful technique that allows us to probe the mechanical properties of the nanoscale world. It's like reading Braille with a tiny needle, but instead of letters, we're feeling for atoms. Here's how it works. A sharp-tipped probe scans the surface of a sample, moving up and down in response to the forces between the atoms at the tip and those on the surface. This movement is then converted into a topographic map of the surface at the atomic level. But it's more than just a map. By analyzing this data, we can also gain insights into the stiffness, strength, and elasticity of the material. It's an elegant solution to a complex problem, allowing us to explore the minuscule from nanoparticles to biomolecules. With tools like AFM, we can probe the nano world and uncover its secrets. Next, we'll discuss the role of phonons in nanomechanics. Phonons are quantum mechanical representations of vibrations in a rigid crystal lattice, like the atomic structure of a solid material. These particles are essential in transferring heat and sound through these materials. But when we shrink things down to the nanoscale, the behavior of phonons changes dramatically, and this has profound implications for nanomechanics. Think about a phonon as a wave moving through a crowd at a stadium. As the wave travels, it can be affected by the size and shape of the crowd. Similarly, at the nanoscale, the size and shape of the material can affect how phonons move and interact. This phenomenon can lead to unique thermal and acoustic properties in nanomaterials, influencing their mechanical behavior. So, when we're designing nanoscale devices or materials, understanding phonons is crucial. Phonons play a key role in dictating the behavior of materials at the nanoscale. You might be wondering, where do we apply nanomechanics? Well, the answer is pretty much everywhere, from medicine to manufacturing, and even in the devices we use daily. In the medical field, nanomechanics is creating a revolution. The mechanical properties of biomolecules such as DNA and proteins are of significant interest. Understanding these properties can help us develop advanced drug delivery systems, improving the effectiveness of treatments and minimizing side effects. For instance, nanoscale carriers can be designed to deliver drugs directly to cancer cells, sparing healthy ones. Moreover, nanomechanics is instrumental in tissue engineering, where nanoscale manipulation and measurement of cells can lead to the development of artificial organs. Beyond medicine, the principles of nanomechanics are also being applied in the field of manufacturing. Nanomotors, which operate on chemical, magnetic, or optical principles, are being used to construct materials on a molecular level. This allows for the creation of products with unprecedented precision and efficiency. A great example is the field of nanomanufacturing, where materials are manipulated at the nanoscale to create high-performance products. In the realm of data storage, nanotribology, the study of friction, wear, and lubrication at the nanoscale is of paramount importance. Understanding these properties can lead to the design of more efficient and durable data storage devices. Even in our day-to-day life, nanomechanics plays a vital role. The touch screens we use on our smartphones and tablets work on the principles of nanomechanics. When we touch the screen, a small electrical disturbance is created. This disturbance is measured and processed, allowing the device to respond to our touch. It's clear that nanomechanics has far-reaching applications, and this is just the beginning. As our understanding of the nanoscale world expands, so too will the potential uses of nanomechanics. From improving healthcare to advancing technology, the possibilities are endless. The potential applications of nanomechanics are vast and varied, and we've only just begun to scratch the surface. As we look to the future, the possibilities for nanomechanics are virtually limitless. This isn't just an optimistic view, but a perspective rooted in the rapid advancements we've seen in recent years. So what does the future hold for nanomechanics? In the realm of technology, we can expect further miniaturization of devices. With the help of nanomechanics, we might be able to create nanomachines that are not only smaller, but also more efficient and powerful than their macro counterparts. These nanomachines could revolutionize various industries, from manufacturing to computing and even space exploration. Nanomotors, for instance, could become the engines propelling nanomachines. Currently, we are witnessing an increase in their efficiency and control, and in the future they might be fueled by light, chemicals, or even biological materials. Imagine microscopic robots powered by atoms, capable of performing tasks that are currently impossible. In medicine, nanomechanics could play a pivotal role in developing advanced drug delivery systems. Nanoscale devices might be able to transport drugs directly to the affected cells, reducing side effects and improving the effectiveness of treatments. Furthermore, we could see the rise of nanorobots capable of diagnosing diseases at their earliest stages, or even repairing damaged tissues at the cellular level. But, as we gaze into the future, we must also acknowledge the challenges ahead. There are still many questions to answer and problems to solve. The behavior of materials at the nanoscale is still not fully understood, and creating reliable, controllable, and safe nanoscale devices is no small feat. Yet despite these challenges, the potential benefits of nanomechanics make it an area worth pursuing. It's a field that encourages us to push the boundaries of our understanding, to think smaller, to go beyond what we thought was possible. And so as we stand on the brink of this exciting frontier, we can only imagine the wonders that nanomechanics will bring. As we continue to unravel the mysteries of the nanoscale, who knows what incredible discoveries lie ahead in the field of nanomechanics.